Waves and particles. We've got two conflicting models. I've just sort of put it off, but today we're going to talk about how these models actually merge. Young did an experiment. Remember, it's always real world observations that have to drive our theories. And Young's experiment verified the theory that light behaves as a wave. There's no other explanation for interference. If we talk about sound, if we were to have two speakers playing at the front of the classroom, that sound, because it travels as a wave, the energy radiates across the room, it hits the whole back wall of the room at the same time. If you were to stand at the back wall of the classroom, depending on the sound from one speaker compared to the other speaker, you may hear it as a loud spot or a quiet spot because of the interference. And the only explanation for that interference is that sound must be a wave. Similarly, with Young's experiment, the only explanation is that light must be a wave. Then jump forward literally like 100 years. Planck is trying to make the light bulb better. He comes up with a theory. Einstein jumps on board and comes up with an experiment to verify it. And we now have an experiment that verifies or shows that light behaves as a particle. So on one hand, the real world is showing light behaves as a particle, and in another experiment, the real world is showing that light behaves as a wave. If we keep going with the particle idea, they didn't have it then, but we've got it now. We've got the technology that we can emit a single photon at a time. So I say we, but universities, workplaces, they have these special lasers that literally shoot out one photon at a time. The fact that we're shooting one photon at a time kind of already implies particle. We now have sensitive enough detectors that detectors can see exactly where the photons land when they get shot on a wall. The fact that we can see photons or little parts of light hitting at a very specific location, we call that localized. When something is localized like that, that's a particle property. Like if I throw a tennis ball at the back wall of the classroom, I'm going to see the tennis ball hit at a very specific or a localized position. That's a particle thing. If I go back to thinking about the speakers in the classroom, if I have speakers playing sound in the classroom, the sound waves are not localized. They hit the whole back wall at the same time. So localized and photoelectric effect are both things that emphasize that light must be a particle. A cool place in science. Some scientists love it when this happens, some it drives them crazy, but we have two conflicting models. When we've got conflicting models, we're kind of at a crossroads. We have to do a little bit of work, and doing a little bit of work should lead to new knowledge. Is one of the models right and the other one's wrong, or do we need a new model? Just as a summary, wave model seems to be right because we see interference patterns of light, and the light's behaving in a non-localized way. It's traveling through both slits and then getting to the screen and creating that interference pattern. And in the wave model, energy is related to that amplitude or the intensity. Particle model seems to be totally different. The photoelectric effect and sensitive detectors kind of show it or verify it. The fact that light shows up as localized, the fact that we can detect them in specific positions kind of verifies that light's a particle. And the math says that the energy is proportional to the frequency, which we see in that photoelectric effect. So is one of those models right, or do we need a new model? If it is a new model, then the new model's got to have aspects of both. Some wave model stuff in it because we do get interference patterns, some particle model stuff because we do have that localized and energy proportional to frequency thing. I'll pause here. What do you think? What's our outcome? Is one model wrong, or do we need a new one? We need a new model. Quantum physics is really a new model of light, a new model of small particles, but yeah, we need a new model. Our new model, it's kind of a cop-out. When I learned this, I thought it was kind of a wimpy way to go, but the new model is just literally, we're going to call it wave-particle duality. A quantum particle, I'll talk a little bit more about what I mean by a quantum particle later, but quantum particles display properties of both models. They follow the wave model and form interference patterns, and they follow the particle model in that they can be localized and their energy is related to frequency. So they kind of follow both. Wave model, interference patterns, particle model, the fact that they're localized. Depending on the experiment, if you set up an experiment that's all about waves, they're going to show their wave nature. If you send up a particle that's all about, or sorry, an experiment that's all about particles, they'll show their particle nature. And there's some experiments where they show aspects of both, which is really cool. Let's go back to the double slit experiment. Instead of pretending we're shooting light, let's say we've got some special machine here that's shooting quantum particles. And again, I'll explain what those are after. Quantum particles leave the source one at a time. So one at a time, little bullets. They travel through the double slit, and they hit a screen back here. There's my screen back there. Because we're shooting them one at a time, the detector, or the screen, this instead of screen, we'll call it a detector. The detector back there can figure out that specific location where they hit. If we could set this up, if we had the technology, other people do, we don't have it at our school, but if we could shoot quantum particles one at a time through a double slit and measure them hitting a screen one at a time, what's crazy about it is we would see an interference pattern. So maybe this was a special laser shooting really, really low intensity light, like one photon at a time, or maybe this was a very cool parallel plate shooting single electrons one at a time instead of a whole big beam of them. But if we could set this up, shooting them one at a time at a double slit and then hitting a detector, we would get an interference pattern on the detector. This could kind of confuse you, kind of bother you. When the first physicists started doing it, it bothered them, and maybe it bothers you now. Here's kind of the questions that should bug you about it. If we're shooting the particles one at a time, there's only one particle out there at a time. It's a particle. It's going to go through one of the slits. So if we've got a particle going through one slit and then hitting this detector or the screen behind it, how does it even know that there's a second slit? How does it even know that it's supposed to form an interference pattern? How does it know not only that it's an interference pattern, that there's these sort of not allowed places where they're not supposed to hit because those are destructive interference? Like if these were little electrons, how do the little electrons know to avoid that position in between those two bright spots, or that position? How do they know that they're not supposed to go there? How did they know to land there instead? It just didn't really make any sense. If they are traveling one at a time and they're making an interference pattern, what the heck are they interfering with? There's only one at a time. So now it gets a little bit weirder. When they saw the interference pattern, experimenters said, okay, we'll figure this out. We've got the technology. Let's just see where they go. So the next sort of evolution in the experiment was, I got to scroll up again, sorry. They put like high-tech detectors kind of right around here and right over here to kind of watch those two slits and to see which slit those quantum particles went through. But when they did that, when they observed the system, the interference pattern stopped forming. So when they put those detectors there, the wave aspect disappeared. They became localized. They went through one slit or the other, and the interference pattern disappeared. It just looked like, imagine throwing a bunch of snowballs or tennis balls through a double slit. You just get a bunch of snowballs behind the one, and you get a bunch of snowballs behind the other slit, and that would basically be it. That's what happened when they put detectors in. The particles seemed to know they were being watched, so they dropped their wave nature and just behaved like regular old particles. How did they know they were being watched? How come observation can change things? But that's the bottom line that we'll see again in other parts of this, as observing quantum systems change the quantum system. They've come up with theories as to what might be happening with these quantum particles. They're different theories. Some of them are out there. There's one that maybe you heard of, it's in science fiction, like the many worlds interpretation. So when our single electron gets to the double slit, it kind of has to decide whether it's going to go through one slit or the other slit. So in one universe, maybe it decides to go through the top slit. In a parallel universe, that same electron decides to go through the bottom slit. Us as humans, we're not in tune with these multiple dimensions, so we don't see it, but electrons are small enough that they can kind of feel the influence of the other dimension. So the electron that went through the top interferes with its sort of twin electron that went through the bottom. So it created a separate universe where the electron went through the other slit, and it still interacts with that other version of itself. That's one of the theories. There's also one called a guided wave theory, but I don't know it as well to speak intelligently about it. But there are theories out there as to what is happening with quantum particles. I've learned a little bit about all of them, but basically the bottom line of each of these different theories is quantum particles are not like regular particles, and they're not like regular waves. They've got aspects of both, so they kind of behave like a particle in that they're localized and we can see where they hit on with our detector. They kind of behave like waves. They're non-localized because they seem to be making an interference pattern. And the thing that other models have in common as well is that if you look at it, if you observe a quantum particle, that changes it. It gets rid of that dual nature aspect. It doesn't behave like both a particle and a wave anymore. But the cool word that they'll use is a quantum particle is in a superposition of both aspects. It's wave-like and it is particle-like. We call it wave-particle duality. When we observe a system, that forces the quantum particle to take on one of those, but until observing it, it's in a superposition of both. This kind of weirdness, this superposition of both until observed, when a guy named Schrodinger was trying to explain it, he came up with that thought experiment about his cat. So Schrodinger's cat, if you've heard about it or want to Google it or read about it, Schrodinger's cat was an attempt to explain the superposition of two very different states, wave-like and particle-like. I use the phrase quantum particles. Quantum particles is just sort of a catch-all. For now, it's kind of technology-based. As double slit experiments get bigger, the list of particles change. But right now, it's really just very small particles. The most common experiments done with this sort of stuff use photons, so little bundles of light, and electrons, because they're crazy small. There are experimenters trying to do this with protons and even bigger compounds like carbon molecules. But for now, it's finicky, so they're working mainly with very small particles. We're going to get into the math a little bit later. I'll sort of give you sort of a threshold of what would behave and what kind of particle would show quantum duality and what particles wouldn't. I've got a list here of, there's Schrodinger's cats mentioned. I've got a list here of videos that I've watched over the years that I think are pretty good. Some of them are just like literally a minute or two long. Some of them, this one I think is like 15, 20 minutes long. Minute Physics is just a couple minutes. So I'm going to pause this video and then we're going to do some math next. But before the math, maybe check out one or two of those listed YouTube videos.